polygons. We know that regular polygons are equilateral and equiangular, meaning all of their sides are congruent and all of their angles are congruent. So we have a formula for the area of a regular polygon, and that formula is area is equal to 1/2 A times N times S. Now this is all multiplication, so order doesn't matter here. You may see this formula as NAS or SAN, but let's talk for just a moment about what these letters represent. So this lowercase a stands for our apothem. Let's draw a quick picture of what an apothem is. So I'm going to draw a regular triangle just because that's the most simple regular polygon to draw. And an apothem, it goes from the center of our polygon and it is perpendicular to a side of the regular polygon. So it is a line segment that goes from the center and is perpendicular to the side. Okay, N, just like in previous equations, stands for the number of sides. So that's relatively easy. If we continue using our example of an equilateral triangle, well, all triangles have 1, 2, 3 sides. So in this case, N equals 3. And S stands for our side length. So that's something that would likely be identified in the problem for you. So if you saw 5 inches labeled, that would be your side length. Now I'll see in just a moment that sometimes we have other things labeled and we have to solve for side length. Okay, so let's work some problems for the area of regular polygons. We're going to start with one that's pretty straightforward. Okay, so our formula is area equals 1/2 A times N times S. And we said A represents our apothem, which goes from the center and is perpendicular to one of the sides. And in this case, we have that labeled for us. It is 6.9 units. N is the number of sides. This is relatively easy to calculate. We just count the number of sides. So 1, 2, 3, 4, 5. We can see that we have a pentagon here. So I plug in 5 for my number of sides. And then S stands for my side length. So my side length is labeled in my diagram as 10 units. At this point, I just have multiplication. All I have to do from here is punch this in my calculator. Now remember, if you're going to punch a fraction in, you need to put it in parentheses so that your calculator will calculate it correctly. When I punch this in my calculator, I should get 172.5 units squared. Remember, this is area, so we're dealing with units squared here. Now, problems 2, 3, and 4 are going to require a little bit more work. So let's look at problem number 2. We can see in this problem we have a regular hexagon. And the only length that's labeled is our apothem. We do not have a side length labeled. But what is special about a regular hexagon is that if I draw in a right triangle here, I know that my apothem created the right angle. And I know that I have a hexagon I know that all the way around was 360. So if I had split it into 6 angles, that'd be 60 degrees each. But I've split it into 12 triangles. You can see that if I created these triangles all the way around, there would be 12 of them. So 360 divided by 12, this is unique to regular hexagons, is 30 degrees, which means I have created a 30, 60, 90 triangle. I'm going to redraw that 30, 60, 90 triangle so that we can see it just a little bit easier. You can see that along the side between the 30 degrees and the 90 degrees, I have my apothem labeled as 6 radical 3 units. So let's see if we can fill out any more information. I know I have a 30, 60, 90 triangle. I know my format for 30, 60, 90 is x radical 3, 2x. Okay, let's take a look at this diagram. So across from my 60-degree angle, that's where my apothem is. So I'm going to go ahead and label that here. So I know that that number is always going to be my apothem. Across from my 30-degree angle, let's see what I have. Across from my 30, just this little piece here. If you look closely, that's only half of a side. So if I have this number, I have to multiply by 2 to get a side length. It's only half of a side. And then across from my 90 degree, I'm going from the center to a vertex. That is called a radius. But in the context of a regular hexagon, let's look closely, I know that my 30 degree, across from my 30 degree is x. Across from my 90 degree is 2x. This is half of side, and 2 of these is a side. So this number also represents my side length. So now we're just going to do a little plugging in. I know my apothem is 6 radical 3. That's given to me. Well, just look at my format. X is 6. So I just plug a 6 in here. Okay, if x is 6, 6 times 2 is 12. So my side length is 12. So now I'm just going to take my formula. Area is equal to 1/2 the apothem times the number of sides times my side length. My apothem, once again, was given to me as 6 radical 3. We know we have a regular hexagon here. Hexagons have 6 sides. And we discovered that each side length is 12 units. So I'm going to punch this in my calculator. Now, I received 216 radical 3 units squared. But I'm going to double check the directions, and the directions say do round to the nearest tenth. So I can say that the area is approximately, and I'll just multiply the 216 times the radical 3, is approximately 374.1 units squared. Just a quick note before we move on to problem 3, it came to my attention that not all of the copies copied correctly, so I want to be very clear that this problem is intended to have an apothem that is labeled as 6 radical 3 units. That 6 radical 3 should be given to you. It should say 6 radical 3. If you can only see the 6, it was just a bad copy, but it should be 6 radical 3. Okay, in problem number 2, we were given the apothem. In problem number 3, we are given a side length. So let's go ahead and write our formula for the area of a regular polygon. It's 1/2 times the apothem times the number of sides times the side length. We know that when we're dealing with regular hexagons, we are going to be using our 30, 60, 90 triangles. We know our format for 30, 60, 90 is x radical 3, 2x. And we know that across from the 30-degree angle, the smallest angle, we have 1/2 a side. We know that across from the 60-degree angle, we have our apothem. And we know that across from the 90-degree angle, we have our radius. But we also understand that since this is 2x and this is 1x, the radius is also the same as the side length. Because this is 1/2 of a side. So as long as I multiply it by 2, I get a side length. Okay, so we were given the side length as 28 radical 2. Okay, so this is 2x. So to go from 2x back to x, I just have to divide by 2. So 28 radical 2 divided by 2 is 14 radical 2. To go from x to x radical 3, I have to multiply by radical 3. So I get 14 radical 6. Remember, this is relatively easy when I have a coefficient and a radical. If I divide, I just have to divide the coefficient. 18 divided by 2 is, 28 divided by 2 is 14. All right, and then I'm multiplying, I just have to multiply the radicals. Radical 2 times radical 3 is radical 6. So now I'm going to plug into my equation. My apothem, I have noted, is 14 radical 6 units. I, once again, have a regular hexagon, so I have 6 sides. And each side length is 28 radical 2 units. So when I punch this in my calculator, I receive 1176 radical 12 units squared. Now, I do want to be clear that if I were asking you to put it in reduced radical form, radical 12 can be reduced. But since we're not focusing on that at the moment, we're just going to go ahead and get our decimal approximation here. And we learn that our area is approximately 4,073.8 units squared. And last but not least, we have one last regular hexagon. In this case, the radius is labeled for us. So once again, we're dealing with 30, 60, 90, x radical 3, 2x. We know this is a 1/2 of a side. This is my apothem. And this is my radius, also equivalent to my side. So my radius is given to me as 12 units. So I know 12 is 2x. So if 12 is 2x, 1x is just 12 divided by 2, which is 6. And I plug this in that format. So this is 6 radical 3. And then I just plug that into my equation. Area is equal to 1/2 the apothem times the number of sides times the side length. My apothem here is 6 radical 3. I once again have a hexagon, so 6 sides. And each side length is 12 units long. So I punch this in my calculator, and I receive 216 radical 3 units squared, which is approximately 374.1 units squared. And I do want to take just one last moment to point out that if you look carefully, problems 2 and 4 end up being the same problem. The difference was, on problem 2, we were given the apothem as 6 radical 3. That is the same regular hexagon where the radius equals 12. Because look at our 30, 60, 90 triangles. They ended up being the same. So become more comfortable working with your 30, 60, 90s.